This is old data. This comes from roughly 2002. You can see the US or the European Ariane launcher, the US Atlas and Delta launchers now are under United Launch Alliance. Obviously SpaceX didn't have the Falcon at that time, but that would go on this chart now. The Russian Dnepr, the Chinese Long March, and also the Russian Soyuz. But you can get an idea. It's about, to buy a Delta is about $55 million. So you want to launch your satellite, you've got a sunk cost of $55 million. You start thinking about what that sunk cost is. You start figuring, I want to get as much mass to orbit as I can because that's a big driver. So that really has driven a number of things over the last 30 years in the space industry. It's driven to going with larger payloads. It's also driven to a huge risk aversion where if you're going to pay that type of sunk cost to get your payload in orbit, you want to make damn sure it's going to work when it gets there. So redundant systems, and the interesting thing is it also inhibited innovation. So people wouldn't fly anything unless it had flight heritage, so it had flown before, and there's no way to get flight heritage unless you can get it on orbit, and nobody's going to fly something that didn't have flight heritage. So there was this circle that really impacted technology development. Something else that's really interesting when you take into account satellite launches, you can see here we've got the solid rocket motors, the liquid rocket motor, and the satellite sits up in the fairing. This is a look inside the fairing. There's an adapter ring here on the upper stage. Then you have the satellite sitting in the fairing. Well, generally, you know, your rocket can only get a fixed amount of mass to a certain altitude. So you cannot show up with a satellite that's too heavy. You won't get into the orbit you designed for. So everybody carries margin early in the design process to make sure you don't go over mass. But the rocket's designed to get a certain amount of mass to a certain orbit. So what you end up doing is you've got excess mass, you add ballast to the system so that you're launching the mass you expected to launch. So think about that. Now you're paying, you know, $50 million for a launch vehicle, and you've got 10% of that that's basically inert mass you're throwing in there because you were carrying this margin. Doesn't seem like a very wise proposition. So one of the things the Air Force did early on in the 2000s, right around 2000, is they developed something called the ESPA ring, which was for secondary payload adapter. So there's a ring right here that adapts the rocket to the upper stage, and they started wanting to put on secondary payloads on here. Well, that's a great idea. Seems like it makes a lot of sense. What's the problem? Well, anybody who's paying $50 million to launch their satellite doesn't want somebody else's rickety old secondary payload floating around in the fairing to have parts flying off and damage their satellite. So, well, in concept, it was a great idea. There was actually problems that nobody actually wanted to let anybody else ride in their satellite, so, or in their launch vehicle. So that kind of drove some new innovations. Along came Bob Twiggs. He was on the faculty at Stanford. This was in the late 1990s, so he was also getting some push from DARPA and from the industry saying, you know, we want to be able to fly new payloads and test out hardware, and particularly test out electronics hardware. So his concept was pretty simple. We're going to take a PC-104 stack and we're going to build a box around it, and we're going to figure out how to get that into orbit. And by building a box around the PC-104 stack, created a cube, and Bob is one of these guys that, you know, knows how to sell things, and so he labeled it the CubeSat, and it was 10 centimeters on a side, so it was basically 1 kilogram, and it took up a volume of 1 liter. Now, there's still a problem. You get these little satellites. How are we going to get them into the launch vehicle? How are we going to solve that problem? Simple. Put them in a box, right? Because what did the primary payload provider care about? They cared about parts coming off the secondary, damaging their primary launch vehicle. Well, you put this thing in a sealed box, you guarantee that nothing's going to come out of the box. You launch, you put the primary into its orbit, then you do a burn, and then you can start popping your secondaries out of the box, and if a pile of parts pops out, the primary doesn't care. They weren't damaged. And so one of the things this did, I mean, it seems very simple, did 2 things. One, it created a standard. You had to fit inside the box, okay? 2, it then drove down risk on the primary so that people started allowing secondaries to come along and launch. And that was really a key development, because before that, there was just people arguing over risk, and you spent all of your time doing risk analysis and not much time doing engineering. So this is a picture of the CubeSat, the first CubeSat that I worked on, we developed. This is the Colorado Student Space Weather Experiment. It's referred to as a 3U CubeSat, so that 10 centimeter form factor is referred to as 1U. You can put 3 of them together to have the 3U that fits inside this launcher here, the deployer, which is a P-pod. These open faces are for access during integration, and then there's panels that get bolted on there. Interesting point, originally we were set up with these 1U CubeSats, and you could fit 3 1U CubeSats inside a P-pod. Well, it didn't take very long for people to say, well, geez, if I can fit 3 in there, why don't I just make my satellite 3 times bigger? And that's sort of what happened. And having a 3U CubeSat sort of, I would say, became more of the de facto standard. People still did some 1Us, but it's hard to get a lot of solar power with body-mounted panels on a 1U. I mean, you're talking about 2 watts of orbit average power. So we're talking really low powers there. And for reference, I tell people that a CubeSat's about the size of a loaf of bread, and it weighs about as much as a gallon of milk. So that kind of gives you a physical reference for what that looks like. A little bit about our Colorado Student Space Weather Experiment. So you can see here, space weather, which I'll talk about in a minute. That's a topic that's been of interest to me and overlaps with my science interests. So the small sat work we've been doing has been related to space weather. And particularly what we were doing with CSSWE here is we had a detector. So this detector detects relativistic electrons and protons. So there's a couple of silicon disks in here. There's a beryllium window that keeps out the low energy particles. And then as a particle goes through the silicon disk, it deposits energy. You can get a charge. The number of disks that get hit, you can use that to infer what the energy range is. And you can see some pictures here of the students doing testing and integration. One of the great things about these systems, not only are they viable scientifically, but they also give students an opportunity to work on spaceflight hardware and get it into orbit. We launched the program. Our project was funded by the National Science Foundation. We launched in September 2012 on a National Reconnaissance Office launch. And our primary design mission was for 3 months. We operated on orbit for 28 months, collected over 100 megabytes of science data, and generated 19 peer-reviewed papers. So we had some great results from this. We actually have some of our data got used in a Nature paper. So fundamental science results. You can see a picture here of the footprints of the radiation belts measured by the satellite. So you can see the footprint of the outer belt here, and then you can see the South Atlantic anomaly that comes down with higher energy protons over the South American sector. So this is a plot taken from some work that Michael Schwarthout has been doing. And he's been tracking all of the CubeSat launches since the beginning of the first CubeSat launches. And I would say, we say picosat launches. So this is a picture from 2000 with the first picosat launches occurred out to 2015. And you can see that there's been a rapid rise in the number of launches. And I'll show you how this correlates. And you can also see who's been launching them. So universities are in green, military, civil government, and commercial. And you can see for about 15, maybe 12 years, we were primarily driven by the universities. And now recently, commercial entities have really got in and started taking over. These first couple of launches weren't actually CubeSat launches. These were picosat. This is a larger satellite, Opal. And you can see they were putting these smaller disk drive satellites inside the Opal satellite and then deploying those out periodically on orbit. And so all of these were Opal deployments, just at different times. The Aerospace Corporation had a launch on the shuttle, and then right here is the first P-pod deployment of CubeSats that occurred on a Russian launch vehicle. This shows a prediction from SpaceWorks of the growth in expected launches. This is actual launches out here to 2014, and then the expected launches 2015. A couple of things I wanted to point out here for reference. This was that first launch here in June 2003. It was actually on a Russian launch vehicle. There were, I think, what did I say, 2, 4, 6, 7 satellites on there. The ones in green operated. The ones in red did not operate. But you can see that the growth rate was fairly slow. Then the P-pod came along, and the growth rate started increasing. And then NanoRacks came along, which is actually a deployer that goes on the International Space Station. And you can see this rapid rise is actually due to the fact that we have almost every other month a cargo supply up to the International Space Station, which allows for rapid turnover and launch of small satellites. In addition to the Colorado Student Space Weather Experiment, we also recently launched another experiment called the Miniature X-ray Solar Spectrometer. This is a picture of the prototype. This is Flight Model 1 that's on orbit right now. This is Flight Model 2 that'll launch in January with the Terabella launch, so formerly Skybox, that was bought by Google. There'll be 3 CubeSats launched on the Minotaur launch vehicle, and this will be the first NASA Science Mission Directorate CubeSat to be launched. As I had mentioned, Minx 1 is currently on orbit. We launched it last December. I got some pictures here. It launched on the Orbital Antares 6 launched on December 6th, went up to the ISS. Again, we're looking at space weather. We're looking at the sun. And particularly, we're looking at the sun in an area called the soft X-ray, so the region of the solar spectrum and the very far ultraviolet from roughly 1 to 10 keV. And this just shows a plot of our data here before the flare, which is the magenta, and then after a flare, which is the white. And so we're measuring flares. We've captured over 3,000 different measurements, 7 M-class flares, 40 C-class flares. If you're aware, we're in the declining phase of the solar cycle, so it's a fairly quiet sun at the moment. We don't have any really tremendous flares, but it's we're actually making some really interesting measurements and excited about this. We're doing it all with students. It shows some pictures here of our student team. Some of you may recognize this guy here, Administrator Bolden, the guy that runs NASA, came and visited when the students were working on the satellite, and they had an opportunity to meet with him. All right, so you can't show a satellite talk without showing a launch. Everybody likes to see the launch. So this is the launch of OA4 out of Kennedy. It's got an ULA Atlas rocket with the Cygnus orbital resupply vehicle on top. And our CubeSat was inside the resupply, so this is the Cygnus resupply. It then separates a couple orbits later, comes and docks with the International Space Station. It gets grabbed by the robotic arm. The astronauts then unload all of the cargo, throw the trash in, send it back out, and it burns up on re-entry. So 6 months later, on May 16th, we deployed our CubeSat. So this is our CubeSat here, Minx, and this is the University of Michigan Cadre CubeSat behind us, and you can see they deploy them down and away coming out of the International Space Station. Then we spent a lot of time in the radio room trying to figure out where our signal is and trying to get communications with the satellite. It's not uncommon that when you have launches from from a single launch vehicle of 10 CubeSats, they're trying to figure out which one of yours can take some time. We spent a lot of time running passes with our ground station out here at LASP, just on East Campus. And one of the things I wanted to talk about is the hardware that we use on our ground station. And so right now, what we use and what most student ground stations use is a pretty similar setup. And the key here is that we're using commercial amateur radio receivers. So this is a Kenwood TS2000. One of the advantages of that, they're fairly inexpensive. They come pre-packaged, tuned up, ready to go in the amateur band. The downside of that is they only work in the amateur band, and you can only track a single satellite at one time, so a single frequency. And so the writings on the wall in the future, and I'll talk about this in a moment, is the software-defined radio approach to satellite ground stations. In fact, some of you may be aware and may have seen this. It was in Spaceflight News, or Spaceflight Now, but Airbus was selected by OneWeb to build 900 internet satellites. Okay, you may have also saw on the SpaceX Falcon Heavy, I guess they call it anomaly last week, that there was an Israeli spacecraft that was destroyed, and Facebook had some technology on there. So Facebook, Google, or Alphabet, and OneWeb and others are getting into these technologies of building constellations of small satellites. And there's a lot of impact when it comes to spectrum, spectrum diversity, and how to manage all of these users simultaneously. In fact, heading to a meeting on Friday in Washington on small satellite spectrum usage that's going to be coordinated with the FCC, the NTIA, and NASA. So it is a big, challenging, growing area. There was a recent report that was very interesting. This came out just this spring. It went on for about 2 years from the National Research Council. It really focused on, what can we do with CubeSats, the type of science that we can do. And one of the things they talked about that was interesting in that report was disruptive technologies. What is a disruptive technology, and why? What does it do to the industry? And one of the things they mentioned is, CubeSats are disruptive technology. And key is that it's an innovation that creates a new market and value network and disrupts the existing value network. And it also, disruptive innovations tend to be produced by outsiders and entrepreneurs rather than the standard class of people working in that field. So if you look at CubeSats, it wasn't the people doing big space who really saw the value of doing this, right? What happened is they actually saw it as being a student project. Hey, don't worry about it, let them go play in their sandbox. Well, it started out down here with having very low performance, a lot of CubeSats not working, but it's grown very rapidly and actually moved to potentially disrupt the current satellite market in ways that have been unanticipated. The PC is always mentioned as a disruptive technology and how it came in and disrupted the mainstream computational market. But high performance computing is never going to go away, right? I mean, the big computing systems at Sandia, the big computing systems that exist for doing high-end simulations are going to continue to exist, but the other end of the spectrum changed dramatically. I think that, as I mentioned, CubeSats are a disruptive technology, and additionally, SDR and GNU radio is a disruptive technology coming in and enabling people to do things that weren't previously able to do, particularly with moving a lot of the RF side of communications into software. So now everybody does not have to be an RF engineer and sit there and understand return loss and S parameters and third order harmonics to get these types of systems to work. Some of the key characteristics of the disruptive technologies, as I mentioned, they have a poor performance. They're significantly cheaper than the status quo. They target underserved or new users. They improve rapidly, and they're induced by a non-mainstream player. And so I think there's a lot of interesting parallels here. And in fact, when I went out and looked on the web and just looked up GNU radio, it mentions that it's a framework that enables users to design, simulate, and deploy highly capable real-world radio systems. But you don't have to be a radio expert to be able to do that. So it enables a whole population of people who previously were not part of this, this group who was developing. I went out and did a Google search as a good academic. The first thing you do is you do a reference search. So I went into Google and Google Scholar and just did a search on the term software-defined radio. And I basically came up with a clear pattern here that started in the early to mid-90s and has grown dramatically in terms of the number of times that term shows up in patents or in papers, okay? And so you can see that there's been a dramatic increase in the types of work that's been out there from this community. I also did a search of software-defined radio in the small satellite conference proceedings. So there's an annual conference in August in Logan, Utah for small satellites. It's grown dramatically over the past 10 years. And you can see prior to about 2004, there was no mention of software-defined radio in that community. And now we've seen an increase up to 10 to 15 papers a year discussing software-defined radio. And here's just a couple of quick excerpts. This is from a paper on the pulsar radio system that's developed by Marshall Space Flight Center, which is a low-cost transponder that's based on the SDR concept. This is a talk that was given by the folks at Tethers Unlimited about enabling software-defined radio technology for high-performance coordinated constellations. I mentioned, we're talking about constellations of hundreds of CubeSats. Think about the communication challenges there to have to manage. And so having a flexible, adaptable, software-defined approach is very appealing. JPL is actually sending a software-defined radio to Mars. They've developed this IRIS transceiver here. It's going to be on the Marco CubeSat. There's 2 Marco CubeSats that will accompany the InSight lander to Mars in 2018. They'll actually act as a communications relay for the lander. Now, the Mars orbiter will be there collecting and storing and forwarding all the data, but there's a period of time where the Mars orbiter is behind Mars, and so we can't get line-of-sight communications, and these 2 CubeSats will actually provide real-time data coming back from Mars. And then this was a great example. This is another National Science Foundation sponsored project. This is actually written up on the EDIS website. So this was one of the second or third CubeSats that was funded and launched by the National Science Foundation. University of Utah built 2 CubeSats again to do space weather. They have a Langmuir probe, E-field booms, measuring parameters of the ionosphere. They used the NASA Wallops ground station 18-meter dish with an SDR, and it says right here that the downlink, during the downlink, the USRP, PC, and storage device was used to record the samples, which would be post-processed using GNU radio and C++. And one of the really interesting things is they ran into a bunch of interference issues early on, but they had recorded all the data, and they kept reprocessing it and kept extracting more and more data out of their telemetry stream as they move forward. So, SDR on a spacecraft, both ground and in space, offers the ability to have a whole range of modulation schemes and being able to change modulation schemes based on channel capacity. One of the things that with a LEO spacecraft is that when it's coming over the horizon, it's at its farthest distance, maybe 3,000 kilometers away, and then it comes overhead, it may only be 500 kilometers away. And so that change in distance changes your link budget. And if you have some adaptability, you can actually change your rate and optimize that link. Typically, the way current radios work is you have one rate and you run that the whole time. So you define your system to work at the least capable rate. So there's a lot of advantages to going to the software-defined radio. I also noticed there was a poster over here talking about sounding rocket and software-defined radio, and I noticed before the meeting started there was a couple of slides up that talked about a couple of companies, Millennium Space, who are doing small satellites and CubeSats. So I see there's an interesting overlap between these communities. So I'm going to move on, and I wanted to just finish up talking about some other interesting concepts. And really, I had mentioned space weather. I'm not going to go into a lot of the details of space weather. It is a important growing field, particularly as we put more and more space assets up into orbit. In fact, the United Launch Alliance has a plan called Cislunar 1000, where they expect to have 1,000 people working in the space between the Earth and the Moon by 2030. So we're looking at operationalizing space, and that means understanding what the characteristics of the space weather environment are. When we look at space weather, there are a lot of different impacts. There are terrestrial impacts in addition to space impacts, impacts on communications, GPS signals, impacts on power grids. And so all of those things are important. And in fact, just recently, this was just this past last fall, that the National Space Weather Strategy was released by the White House, by the National Science and Technology Council, and so there is a lot of work growing in this area. This just gives you a quick overview of the Earth's atmosphere to give you a feeling of scale. So down here in the troposphere at 10 kilometers is typically where commercial aircraft travel. We move up to the stratosphere where the ozone layer is, and then the mesosphere up here at about 100 kilometers. And what I want to point out is this is the meteor region. So one of the other things I do work on is on meteor radar, and I just wanted to kind of point out some of those points up there. The National Science Foundation, in doing space weather, operates a number of very large radars, 4 radars listed here around the world. One of the things to note is that all of these radars use some aspect of software-defined radio for capturing their signals and analyzing their data. This is the system at Millstone Hill, uses a software-defined approach and actually has a gigabit backbone and pulls off data at different taps for different purposes. This shows a picture of some of the data that comes out of the Millstone Hill radar. This is from 100 kilometers up to 500 kilometers. This shows the background electron density, the background electron temperature, and ion velocity. And if you want to talk about that more afterwards, I'm happy to explain the details. One of the things that I've done for the last 20 years is worked on an area of meteor radar. This is a wonderful picture. It shows the aurora space weather impact with a beautiful meteor in the background. We can actually scatter we can scatter radio waves off of meteor trails to measure winds at 100 kilometers. Okay? Talk about space weather. Well, winds are something we need to know. This shows a simple typical meteor return. This is range and distance in kilometers, and this is time. These are what we refer to as underdense meteor echoes showing up here on the order of 10 or 15 dB signal noise ratio, and this is what's called an overdense meteor echo. And again, I won't get into the physics of that. We run our systems with 5 different channels, so we can do interferometry to find direction of arrival and look at the phase relationship between the signals. And we essentially run a software-defined radio system. So we have this is a fully integrated radar system. So we have 8 channels of receive. We have 8-channel analog digital converter. We run our signal processing in an FPGA and push it out. We have 4 different synthesizers here generating our signal, and then we drive out the RF signal, and it's all calibrated. It's a bit of a spaghetti box, but you can see here what that system looks like. We've taken this into the field to 6 different sites and collected meteor data on it. One of the other really interesting things, and this is some of my other colleagues, and so again, I just want to highlight some of the other work that's been going on in terms of remote sensing and software-defined radio that you can think of. This now looks at meteor trails instead of in a simple backscatter configuration and a forward scatter configuration. This comes from colleagues Gunther Stober and Koki Chow at the Institute for Atmospheric Physics in Königsberg, Germany. This approach, they can now get an increase in the number of meteors, but they can also get a diversity in terms of the coverage that they're seeing these meteors from. And from that, they can get these vector wind fields for the first time. So now we can start getting basically wind maps of the winds at 100 kilometers to use for these space weather applications. Another colleague, Julio Urbina and Frank Lind here, have developed another software-defined radio approach for looking at plasma instabilities. Again, USRP, GNU radio, it just sort of gives you an idea of the breadth of type of work that the remote sensing community is doing, and also you can see that these are getting published in radio science. And this just shows the concept of the passive radar where we have a single reference antenna and an echo receiver, and you're looking at a separate transmitting site. And then lastly, colleague Juha Virtanen has been doing some work looking at beacon receivers. So now here you have a satellite. It's transmitting an HF signal. As it comes overhead, you have receivers on the ground, and you measure the path. You can look at the amplitude and phase. So you can look at the amplitude attenuation and the phase retardation through the system. And as Juha puts out, the data recording portion of the software is written using the GNU Radio open software framework, and this gives you some idea of the type of electron density results that he's getting. So I just wanted to wrap up. I know I've gone over a lot of things in a fairly high level, and what I was trying to do was raise awareness for some of the work that's going on in the small satellite community and also in the remote sensing community, and understand that the value that GNU radio and software-defined radio plays in both of these communities. I always love this quote by Norbert Wiener, and for those of you that are from the signal processing community, you're familiar with Norbert Wiener. It's the boundary and the regions of science that offer the richest opportunities for the qualified investigator. So it's those crossovers with communities that are really great. So just to finish up, some closing thoughts. I see the GNU radio SDR technology as a disruptive technology similar to the CubeSats. There's a lot of different opportunities. I talked about a couple of them here. And you are the experts in the software-defined radio community and GNU radio. Spend some time, find a scientist. They don't have all of the expertise they need to accomplish some of these interesting problems, but they have lots of interesting problems. So, think about how you can coordinate with them. Again, enjoy your week on campus, and with that, I'll take any questions. Thank you. Do you want to pass the microphone? I'm not sure how you're doing questions.
Yeah, oh, there we go. Okay. Would you mind coming up and grabbing this one and then passing it around? Hello? Hello? There we go.
Hi. I was just wondering if you knew, is there a wish list of things that people want small satellites to do?
It's huge. Somebody told me recently that there's been upwards of $1 billion invested by venture capital into the small satellite community, and I think what the big driver is. You see places like OneWeb looking at small sats, and that's really about providing internet capability, ubiquitous internet capability around the globe. But there's a lot of interesting change detection, situational awareness. Planet Labs is flying constellations of CubeSats with 10-centimeter telescopes. The diffraction limit on the ground is maybe a 5-meter ground pattern. So you can't do lots of, let's say, detailed imaging like you can with digital globe satellites, but what you can do is look at change detection, and which has been very valuable. So there's a lot of humanitarian change detection programs that are being looked at, and then constellations for space weather and distributed Earth observing constellations. One last one I'll mention is MIT Lincoln Lab is flying a radiometer, and they've shown that with this radiometer that they've developed, if they can fly a constellation of 12 of them, that they can have a measurable impact on our long-term weather forecast by using these radiometers to measure the water content in the lower atmosphere. So that's kind of the feel of where things are going with small sats.
Hi. Yeah, it was a great talk. Thanks for that. And one of the things you mentioned was how easy it is to get into this whole GNU radio and SDR. And I was wondering if you had any thoughts about random people that are not full-time researchers or academics being able to participate in, well, either like ideally the whole CubeSat thing, but SDR in general. If you have any specific ideas about what random people from the population could do to participate in that, I'd be interested to hear your thoughts on that.
Yeah, so I think there's always opportunities. It's a matter of trying to find them, right? They aren't often advertised. It tends to be networking types of opportunities where I'll give you an example with my CubeSat class. I have people in the satellite industry and other full-time jobs who come as advisors for the students and bring that type of expertise and participate in helping to develop the students. And so there's those types of partnerships, and I think virtually every university is open to developing those types of partnerships. It's a matter of trying to figure out who to talk to and how to get engaged. And so one of the things, particularly with CubeSats, is to look at your home institution, look at your state, and I think every state in the country has a space grant, a NASA space grant consortium, and so that's a place to get started. They can be a pointer to help you understand what sort of opportunities there are locally. The other thing is, if your university host IEEE meetings or AIAA meetings, that's a place to network to get to know some of the people who are working in that community.
Okay, we're going to do one last question here, and then we're going to move on. Oh, here it is. So whether you're flying large satellites or CubeSats, communications is a really important factor. You mentioned you're going to be in DC talking about spectrum. Really briefly, as far as innovation and enabling what you've talked about here, what do you see as the right direction to go on a spectrum policy front? Thanks.
Wow. That's a challenging question. I will say that I am not a spectrum expert. I will say my personal belief from at least the small sat community is to move away from this 1960s ITU vision of spectrum where everybody gets their slice and we've got to coordinate every single satellite that goes up and give people their frequency allocation, because one of the challenges is that process with the FCC and the ITU for satellites can take 3 or 4 years for coordination. We're talking about turnaround times on small satellite systems to launch that could be 9 to 15 months. So there's a disconnect there. So the idea of having spectrum where we've got some sort of code division, multiple access. So you could give people, say, look, this is a chunk of spectrum that small sats or that fast turnaround small sats should operate. Yeah, here's your code. You're now not going to interfere with the other guys. Go, and everybody can design hardware to operate in that piece of the spectrum. So that's at least my current thinking for small satellites. But there's a lot of other pressures and operators. Just my opinion. Yeah, thank you.
All right, let's thank our keynote speaker. Thank you so much, Scott.
Thank
That
you.
was really great.